This video is sponsored and approved by CuriosityStream. Antimatter. It might sound like the stuff of sci-fi. The engine of the Starship Enterprise in Star Trek is powered by antimatter. The bomb in Angels and Demons that Tom Hanks races across Rome to stop is apparently made of antimatter. Why, even Rick from Rick and Morty apparently makes antimatter guns. But antimatter is actually a real thing. It's part of the natural world. It's just incredibly rare, vastly outnumbered by normal matter, which, physically speaking, is really weird. So to study it, we have to be able to make some. And for that, you need the huge particle accelerators like they have at CERN in Switzerland. I'm here at CERN all this week, and I'm going to be chatting to the scientists who are working on the antimatter experiments here to ask them, what is it? Where is it all gone? Before we go find some particle physicists here though to pepper them with questions about what cool science they're doing, we should probably brush up on what exactly is antimatter. So antimatter is the exact opposite of normal matter. And what that means is that for every property of a normal matter particle that you can measure, its antimatter particle has the exact opposite value of that. So for example, a proton. It has a positive charge of +1, we say. But its antiproton has a negative charge of -1. And you can do the same thing for an electron as well. Its antimatter particle is called a positron because it's not negatively charged like an electron, it's positively charged. But what does all this mean, and why do we even care? Well, antimatter was made in the Big Bang at the same time as all the protons and electrons and neutrons, the stuff that makes everyday normal matter around us. At the same time, all the antiprotons, antineutrons, and anti-electrons, we also call those positrons, were also made. So how come everything around us now, including me, the floor, this camera I'm recording on, is now made of normal matter, not antimatter? Well, when an antimatter particle and a normal matter particle meet, they annihilate. And that's not an exaggeration. It really is doomsday levels. They turn back into pure energy. Essentially, we get light, gamma rays, out of that annihilation process. So somehow everything we see around us has managed to avoid coming into contact with an antimatter particle in the early universe, which suggests that somehow there was more matter made than antimatter. So the question is, where has all that antimatter gone, and why was more matter created in the first place? So to answer this question of where has all the antimatter gone, people at CERN are trying to make some antimatter in order to study its properties in relation to normal matter. But don't worry or anything, they're not going to make loads of it like they do in Angels and Demons, because even the antimatter they make here at CERN is made in minuscule amounts. Like it only adds up to something like a nanogram of antimatter. Compare that to the 2 nanograms of positrons made at DESY in Germany and the 15 nanograms of antiprotons made at the Tevatron Fermilab in Chicago. In fact, if you took all the antimatter ever produced by humans in the history of antimatter research and you annihilated it all at once, you wouldn't even have enough energy to make a cup of tea. So antimatter is rare, definitely, especially in comparison to the amount of matter in the entire universe, since, well, it doesn't go very far until it encounters a normal matter particle and it annihilates with it. But the production of antimatter isn't exactly rare in itself. In fact, every time you eat a banana, you're eating some antimatter. So bananas contain potassium. It's the reason we're told to eat them, right? It's a health benefit. But potassium also has an isotope, which is radioactive. So an isotope is where you have a normal atom of potassium, but you've shoved a couple of extra neutrons into the very center in the nucleus, which has made it unstable, which means it radioactively decays. And when that happens, it gives off a positron, the antimatter particle of an electron. It's just when that happens after you've eaten the banana, you don't exactly notice the amount of energy given off when it annihilates with another electron in your tummy. Almost makes you kind of question why they even bother like building these huge detectors to make antimatter when they've just got bananas lying around everywhere in the canteens, just like giving off positrons. So if you're not a banana, how do you actually make antimatter? Well, CERN has the largest science experiment in the world in the form of a 27-kilometre long circular tunnel, 130 metres underground, which spans the border between France and Switzerland. And in that tunnel, protons are accelerated to close to the speed of light in two beams which travel in the opposite direction to each other. And in a few places along that tunnel, there's areas that you can bring those two beams together so that they collide, and then there are detectors there to record the fallout from those collisions. One of those detectors is the Lhcb experiment, and its main focus is studying the differences between matter and antimatter. I've got Lhcb particle physicist Mark Williams to take me down underground to see the detector. It's a really heavily secured area and you need a retina scan to access it. Now, you can't quite actually capture the scale of this thing on film. It didn't even feel like I was underground at the time. Like, the cavern was so vast, as you can probably tell from my rather stunned and speechless expression. I chatted to Mark in the Lhcb control room afterwards when we made it back up to the surface about what the Lhcb experiment is actually trying to do.
Basically what we're trying to do, and this is a bit of a cliche, is recreate the kind of processes that happened shortly after the Big Bang. So by colliding protons with very high energies together, we can produce both particles and antiparticles randomly. This is quantum mechanics, so there's some probability of producing a Higgs boson, there's some probability of producing a top quark. If we do this often enough, we can get a good collection of all of the various types of particles and the antiparticles, and then we can compare them. So fundamentally, it's random, right? It really is random. This is quantum mechanics at work. We don't know for any given collision what's going to happen, but when you collect enough collisions, on average, you can compare what you see with the predictions.
I was like a kid in a candy store in the Lhcb control room, especially surrounded by huge boards with these big red buttons to press. And I think Mark knew I was overly excited as well, so he treated me to a little bit of Lhcb astronomy trivia.
We're actually affected by the moon, among other things.
Okay.
The beams, when they're circulating in this big ring, they spend a long time traveling around, and it's a big ring. And obviously the tidal forces on the Earth from the moon can distort this ring's shape. And so we can actually see the beams moving with respect to the ring, or rather the ring moving with respect to the beams from the moon.
So the collisions in the Lhcb detector essentially give us a random particle generator. But how does that let us probe the differences between matter and antimatter and get at this question of where has all the antimatter gone and why? I've come to talk to Lhcb particle physicist Tara Nanu to find out how.
So if you can look at the Lhcb logo, you can see it says Lhcb and then it's mirrored.
Yes.
And the CB mirrored becomes CP and there's a slash over it.
Yeah.
Now that's actually a very cool trick that tells you what our experiment is about. It's about CP violation. So the slash means violation. Now that's our fancy term, or the physicist term, to essentially say we're studying the differences between matter and antimatter. So for us, how matter and antimatter distinguish themselves is through charge and parity. So matter becomes antimatter if you flip its charge and if you flip its parity. Now, if there was a perfect symmetry between matter and antimatter, then CP would be a symmetry. But we know that's not it, so what we're studying is the violation of this symmetry. So whenever you hear a physicist say CP violation or CP asymmetry, or you find an article that talks about it, this means the difference between matter and antimatter. This is what we're studying. This is the main goal of our experiment, actually.
So how do you even test for this weird asymmetry between matter and antimatter?
So measuring decay rates is one way. So it's very simple. If one particle of matter decays in one way more often than its antimatter particle decays in its, let's say, analog way, then you obviously measured this. So for every process like this that involves matter, there's an opposite process involving antimatter. So what then the simplest way would be you try to measure the rate So the frequency of the events involving matter, and then the frequency of the events involving antimatter. Now, if there's an asymmetry, which we know in many cases there is, you will measure a different rate. You will see, okay, matter decays are more frequent than antimatter decays. So that's one of the simplest possible ways to measure. Of course, that often doesn't cut it. So we have to go about inventing new and new possible ways, very indirect, to study this phenomenon.
So, the LHCb deals with decays of antimatter and matter particles, which happen in less than the blink of an eye. But what about properly making and storing some antimatter? Well, that's the job of the Antimatter Factory, and particle physicist April Cridland as well, who's come to show me around this building with the best name in the world.
This entire building is actually a decelerator. So everywhere at CERN, we're trying to go faster, faster, faster. And this is one of the few places where we're trying to go as slow as possible. So it's completely the opposite to everywhere else you're going to see. And we don't rely on anything here running on the LHC, which is also surprises people. So we run from what feeds the LHC, called the proton synchrotron. And that's going really, really fast, spinning protons around the ring. And then those protons, they smash into a target. And from that target, we get antiprotons. So everyone in this building wants to work with antiprotons. So what we're interested in alpha is making antihydrogen. So hydrogen is one of the simplest things you can look at on the periodic table. It's also incredibly well studied. So we know the theory of it. We have countless experiments that measure all these properties of hydrogen to really, really high precision. So if we can do the same with antihydrogen, we can then maybe start to look for some differences. We can say, okay, are there any differences between matter and antimatter? So we hope to find some little difference somewhere that gives us a clue to how we might change the standard model, which is an excellent theory of how the universe works and all the particles come together, but it just doesn't explain this imbalance of matter and antimatter.
So, unfortunately, we still don't have the answers to that question of where has all the antimatter gone, hence why this video is an unsolved mystery video. But as an astrophysicist, whilst I was there, I couldn't help but ask April about how gravity affects antimatter as well.
So we have two experiments here that are trying to study how antimatter behaves in a gravitational field. So we've known for a long time that if you're holding an apple, say, and you drop it, it falls to the floor because of gravity, right? We're happy with this, we learn it at school. But no one's actually tested, what if you had an anti-apple and you let go of it? Yeah, what would it do? Will it go up? Will it go down? Will it do it at the same speed? No one's actually measured it. So there's G-bar, which is just over there, which aims to do a gravitational measurement in free fall. But there's also Alpha has built a brand new experiment, 2018, called Lhcb. So what we hope to do is create antihydrogen the way we normally create it in Alpha, and then turn our magnets off, let it go, and see what it does. See if it goes up, see if it goes down, see if it travels with the same speed. We can currently make over 1,000 antihydrogen atoms in 8 hours. But what we need to do is really need to understand the magnets within our system very, very well to be able to then be sure what we're seeing. Of course, if we let it go and it went up the first time, we'd be very dubious about that and be retesting the system again and again and again until we were confident.
That's so cool. It's always the thing I've wondered about is would you call it anti-gravity, do you think, or?
Some people use the term anti-gravity. We're holding back at the moment until we have something worth saying, and then we can see.
The fact that we as humans, as a species, have managed to come up with and design experiments that allow us to answer questions like, where has all the antimatter gone, absolutely astounds me. Like, you can't help but be inspired by this place and the people who work here, who are just so excited and enthused to be working with other like-minded people who care about questions like this. So when I look around and I see the people working here and I chat to them, I can't help but feel like the question of where has all the antimatter gone is not going to remain an unsolved mystery for long. So before we get to the bloopers, I just want to say thanks to today's sponsor, CuriosityStream, without who this whole trip to CERN wouldn't have been possible. CuriosityStream is a streaming service of documentaries and non-fiction films on pretty much any subject you can imagine. So if you want to learn more about particle physics after watching these videos in more detail, then they've got you covered. I particularly liked this documentary on dark matter and the hunt for it because, you know, as astrophysicists, we're still waiting for the particle physicists to figure out what it is already and tell us. I haven't covered dark matter on this trip to CERN, so if you want to know more about the particle physics behind dark matter, search for it on CuriosityStream and check out this documentary. Best thing is, it's only $2.99 a month. And for my subscribers, enter the promo code Dr. Becky, that's DRBECKY, when prompted during the sign-up process, and your membership is completely free for the first 30 days. So click the link in description and check them out now and give them a big thank you from me for funding my dream trip to CERN. But what would you do? What is it? Blah, blah. Words are hard.
One thing that really is true is if something's broken, almost every solution is some form of turn it off and on again. And it almost always works.
That makes me feel so much better in life.
You know, we have the soft turn it off and on again, the medium, and then the hard turn it off and on again.
Nice. The fact that we humans as a species, words are hard,